Hello everyone, my name is Maxwell, and I'd like to overview my group's work on thermal energy harvesting inside vacuum insulation panels. So I'd like to begin with a brief outline of what I'll be presenting today in my 15 minutes, after which please feel free to ask me any questions. I'd like to begin with a brief introduction of the project, and I'd like to begin by introducing vacuum insulation panels, which are the main application of my research. So vacuum insulation panels are the most efficient building insulation material, and they consist of a nearly gas-tight chamber filled with a support material and a vacuum surrounded by aluminum foil or a gas impermeable barrier. And as a result of this, the thermal resistance, or the R value, is 6 times that of extruded polystyrene or conventional foam insulation, which is a more common material. However, there are a few problems with vacuum insulation panels. The first and foremost is vacuum leakage, because if the vacuum can leak over the building's lifetime, and if it does, then the panel loses its insulation effectiveness. And as a result, to remedy this problem, we have to monitor the panel's vacuum over the building's lifetime and alert maintenance crews when the panel needs replacement. So our group solution is to install sensors inside each panel to monitor the panel's pressure over the course of the building's lifetime. And this sensor would have to be powered over the course of the building's lifetime, which isn't 10 or 20 years, it's closer to 50 years. And as a result, chemical batteries are not sufficient, and running wires to each insulation panel is, of course, infeasible. So our group solution is to utilize the temperature difference that naturally exists across the insulation panel to power our sensor. So now I'd like to talk about the thermoelectric generator, which we use to power our sensor. So the thermoelectric generator uses the Seebeck effect, which states that if you have a semiconductor material and there's a temperature difference across your semiconductor, then charge carriers will tend to migrate from the hot side to the cold side, which generates a small voltage. And by wiring tens or hundreds of these semiconductor legs electrically in series, then you can generate a more usable voltage. So there are several criteria for selecting TEGs. The first is the Seebeck coefficient, which dictates the voltage that you can generate given the temperature difference. As you can see in the first equation, V equals S times delta T. So we want to generate as high a voltage as possible, so we'd like to optimize for that. And there's also the electrical resistance, which dictates the power you can harvest at the maximum power point of your equation, of your TEG. So as you can see in the second equation, power equals the voltage generated squared divided by 4 times your electrical resistance. And the third criterion is the thermal resistance, which dictates how long a temperature difference can be maintained across your TEG. And we think that this is probably the most important criteria for our particular application. And the most suitable TEG is a trade-off between these characteristics, and we optimized for thermal resistance by selecting a TEG with a smaller surface area and a greater thickness. So that's a brief overview, and I'd like to talk about weather simulations that I did to approximate how much power I can generate using TEGs. So we wanted to model power generation over the course of the year by month, and over the course of day by hour, based on historical Boston weather data. So for monthly temperature data, we averaged the temperature highs and lows for each month from 2005 to 2015. And for hourly data, we averaged the hourly temperature data for the year 2015 by month. And then we calculated a temperature difference between inside and outside, assuming a constant room temperature of 22 degrees C room temperature, from which we got the voltage output using the Seebeck's law, from which we calculated the power generation at the maximum power point. So now I'd like to show some of the data that I got. The leftmost graph is the average monthly temperature. As you can see, temperature is lowest in January and hottest in summer. That's not what I'm trying to prove. but observe that the temperature difference is greatest in the winter months and smallest during the spring and summer months. That's what we're looking after. And the rightmost graph is the monthly peak voltage derived from a temperature difference. And as you see, based on the temperature difference, the power generation is greatest in winter and smallest during the spring and summer months. So now I'd like to show the power generation graph. So, and likewise, power generation is greatest during winter, smallest during spring and summer, and the difference is exponential. And this is our monthly data. Now I'd like to show our hourly temperature data. So this is a graph of over the course of the day of the temperature, and the temperature curve is more or less the same over the course of the day by month, except just offset for each month. And I'd like to show the power generation curve. And an interesting trend I'd like to point out is that in the winter months, peak power generation occurs in the early morning when it's coldest and temperature difference is greatest. Whereas in the summer months, peak power generation happens in the late afternoon, when the temperature is highest. However, it's harder to see this. So now we have an approximate figure for how much power we can generate over the course of the day and over the course of the year. Now I'd like to talk about the thermal chamber tests, which we did to determine the best experimental setup for harvesting power. So this is a diagram of our setup. We use the thermal chamber to maintain a temperature difference between inside and outside, and we used a thermoelectric generator to harvest energy, connected to varying amounts of heat sinking, and to alter the thermal conductivity between the TEG and the surrounding environment, which I'll talk about in the next slide. We measured open circuit voltage and conducted a voltage sweep and measured current to get a power curve and determine the maximum power level. And for the thermal chamber, we used two temperatures. We used 30 degrees C and 40 degrees C. And I'd like to show you the heat sinking characteristics that we vary. So we used aluminum legs to thermally connect the TEG with just the exposed VIP surface and also with one aluminum sheet and two aluminum sheets. So gradually increasing the amount of heat sinking and thermal conductivity. And finally, we also removed the aluminum legs and thermally isolated the TEG. So as you can see in the picture, the TEG is small. It's about 6 millimeters by 6 millimeters squared. And then it's being sandwiched by two aluminum legs and connected to the VIP panel. And as expected, our results showed that with more heat sinking, we got more power generation. So thermally connecting to two aluminum sheets provided the most power. However, also connecting to the VIP surface directly also yields significant power generation. Now I'd like to talk about the window tests, where we actually took our setup from this past experiment and inserted it into a window to measure real-life power generation. So we inserted the setup inside a conventional UPS foam insulation panel into a window and measured the same criteria in addition to temperature over the course of the week. And we also temperature regulated the room to 22 degrees C, just so we get fairly reliable readings. And now I'd like to show you the data that we received. So it's a bit overwhelming, but the red line and blue lines correspond to the right axis. Red line is outside temperature, and the blue line is the inside temperature. And the green line corresponds to the left axis and is the power generation over the course of the day. And the dark green line is average power. So a few trends I'd like to point out. As you can see, when the temperature difference is smallest at about nighttime, power generation is also smallest at nighttime. And power generation peaks in the middle of the day because this happened. I should mention we did these experiments over the course of the summer. And peak power generation happens in the middle of the day and peaks at about 5 o'clock. And we calculated the average power generation over the course of a summer day to be about 28 microwatts, which is sufficient for a small sensor node application. So now with this power figure, we moved to powering an actual sensor using these approximate power figures. So for proof of concept, we used a hot plate at 35 degrees Celsius connected to the TEG. And we needed an energy harvester in order to get usable power because we can't power from such small voltages. And we used an LTC 3108 demonstration board that actually stores energy in ceramic capacitors so we can duty cycle our measurements. That is, take our measurements periodically. And also it has a 20 millivolt cold start voltage, which is perfect for this type of application. And has a 3.3 volt output and a power good pin to dictate when the output voltage is within a tolerance. And our load board is a microcontroller board with an 8-bit PIC microcontroller with an onboard temperature sensor and 900 megahertz radio. So there's also a switch connected to the power good pin on the LTC board that cuts power to the microcontroller when the output voltage of the LTC board is not within the tolerance. And our program running on the MCU measures the temperature and the voltage of the source and transmits the data over 900 megahertz if the voltage is greater than 3.2 volts, just an additional threshold. And here's a picture of our setup. As you can see, we have a hot plate, which also you can see in the right picture. And the TEG is the faint blue speck on top of the hot plate. It's fairly small. And we have it connected to a heatsink and cooled with a fan. And that's connected electrically to the LTC board, which is the green circuit board on the right. And we are also measuring V-store, the power good and voltage out voltages using multimeters, and also receiving the wireless packets and processing them on the computer on the right. So this is a picture of our the multimeters. The V-store pin is the storage capacitor voltage, and that should be as high as possible. The V-out voltage should be as close to 3.3 volts as possible. And the power good pin should be a constant 2 volts unless the voltage dips below 3 volts. And we determined the maximum power point of the TEG to be 24 millivolts and 6 milliamps, so about 150 microwatts. And under these conditions, the sensor transmitted every 2 seconds, which we determined is more than sufficient for our particular application. In summary, we proved that thermoelectric energy harvesting for buildings is feasible and can power a wide range of ultra-low power sensors and IoT solutions actually embedded inside buildings. And monitoring VIP pressure is just one out of many use cases. And to do, we still have to power the sensor using a TEG embedded inside an insulation panel. We completed a proof of concept, but still have to test this in real life conditions. We also have to create a custom power good circuit because we noticed that sometimes the PGA circuitry cut power in the middle of a transmission, destroying the packet. And we're also looking into using an actual pressure sensor inside a VIP and exploring additional use cases for embedded sensors. Thank you for listening to my presentation. Any questions?
Any questions? Yes, two actually. Right. So, you said you did the window testing, right?
Yes.
And you mentioned something about it's somewhere in the summertime. Is there a specific reason why you picked that, or is it just the middle of the project?
Yeah, I actually did my work over this past summer at MIT, and so we had to do the experiment over the summer.
Oh,
And in the future, I'd also love to get a winter, insert the panel in the window during winter, get power.
Yeah, that's all I'm asking my second question. Because there's all the setup and all the equipment's done in high school, or is it at MIT?
My entire experiment was done at MIT.
Oh, because it was in high school, I would love to go to high school. Thank you.
Yes.
So how is the power output for the little TEG compared to maybe like a small solar panel of similar size?
The TEG output is smaller than a solar panel output, but the solar has many constraints. For example, it can't generate power if it's embedded inside the wall of the building. But a TEG should be maintenance-free and installable anywhere. Like, I should say that TEGs are currently used for waste power recovery for like large engines and power generation applications. But actually using them for small temperature differences like I'm doing is a new use case.
Any other questions?
So just a quick question. So the foam insulation that you use, you said it was, I think, 6 times greater than the typical insulation that's used. What about cost? Is it going to be a practical use case for that type of insulation to use?
Great question. Yeah, VIPs do cost more than conventional insulation, but for places with extreme temperature differences, like I don't know, like the Baltic countries, then actually in Scandinavia, VIPs are already used extensively for commercial applications because the cost of the energy savings justify the cost. But I do see in the future with increasing adoption that VIP costs will